Indeed, the solution of Kohn-Sham equation is desirable. The input of Kohn-Sham equation is potential, and by solving it, the energy and the wave functions are obtained. Summation of all of these parts is Hamiltonian that depends on carrier density. As we said before, the total potential is a summation of nuclear potential, Hartree potential, and also exchange correlation potential. This is the flowchart of self-consistent field calculation. See the flowchart. At the first step, the nucleus potential is constructed. Then electron density is guessed. Indeed, the potential that an electron feels is not only nucleus potential. From the quantum theory, we know that an electron also feels potential due to other electrons. We call it Hartree potential. This potential is called self-consistent field potential, and in this flowchart is the summation of Hartree potential and exchange correlation potential. The summation of nucleus or ion potential with self-consistent field potential is named effective potential. After the definition of potential, the Schrödinger equation should be solved. You can see the Schrödinger equation here. At first, an initial electron density is guessed. Hartree potential is a function of electron density. Thus, by defining the initial electron guess, the effective potential is constructed. As we said, the effective potential is the summation of nucleus, Hartree, and exchange correlations potential. By solving this, the energy values and also wave functions are obtained. By using wave functions, the electron density are computed. By using electron density, the self-consistent field potential is calculated and the loop is repeated again and again until convergence occurs. When the energy error becomes lower than convergence threshold, the convergence is achieved. We should define the convergence threshold in the quantum espresso input file. We set the parameter of convergence threshold to be 10 to the power of minus 6. You should note that in the flowchart loop, usually the new and old value of charge density is mixed. We control this by mixing beta parameter. For example, mixing beta equals 0.3 means that 30% of density from new density and 70% is from old density. As we said before, we can use PWGUI interface to create an input file. In the terminal environment, I write ./PWGUI. We choose File and then new pw.x input. To do self-consistent field calculation, we specify a title, then we choose the type of calculation. We can see many types of calculations here, such as self-consistent field, non-self-consistent field, band analysis, or relax analysis. We choose self-consistent field. Also, we choose restart mode to be from scratch. As we said, we specify the directory for input-output files, the location for wave function file generation, and also a directory where the downloaded pseudo-potential file is located. Also here we should specify the prefix. After the Control tab, we go to the System tab. As you can see in the lattice specification section, we specify some information about the lattice. For graphene lattice, we can choose hexagonal lattice or monoclinic lattice. In this section, we can choose different types of lattice. You can see simple cubic, face-centered cubic, or hexagonal, or monoclinic. I choose monoclinic. Then we should write the magnitude of lattice vectors here. I mean A, B, and C. From graphene physics, we know that values A equals 2.452. Also B is 2.452. And C is considered to be 8 times of A and B. C equals 20. As you can see, the graphene lattice, the angle between A and B, I mean the angle between these two vectors, is 120. Thus, the cosine is equal minus 0.5. Thus, we write it here, minus 0.5. The number of atoms in the unit cell. As you can see, the graphene lattice, in each unit cell, there are two atoms, this and this. Thus, the number of atoms in unit cell is 2. Thus, we write it 2. In the unit cell, only there are carbon atoms. Therefore, the number of types of atoms is 1. Energy cutoff for wave function and cutoff energy for density are two important parameters. I will explain them in separate lecture. Then we go to the optional variable tab. For input DFT, we should define exchange correlation type, that we should define this according to pseudo-potential file. In our case, as I said before, the exchange correlation type is PBE. Thus, we should write here PBE. Occupation depends on the type of calculation. For self-consistent field calculation, we choose smearing, which means a smear occupation by some function such as Fermi-Dirac or Gaussian. For another type of calculation, for example, density of state calculation, we choose tetrahedra. Now for self-consistent field, we choose smearing. As I said, we can choose the type of functions here to be Gaussian, Medfessel, or Fermi-Dirac. Our choice depends on the type of material that can be semiconductor, metal, or insulator. These functions have values between 1 and 0. That 1 means full occupation and 0 means non-occupation. The slope and characteristic of their transition from 1 to 0 or vice versa are different. Fermi-Dirac uses the exponential form to estimate occupation, Gaussian form to estimate the occupation. Medfessel smearing uses some mathematical series to estimate it. We choose Gaussian smearing. Also, the dgas parameter defines the smearing width. A small dgas has better accuracy, while large dgas needs fewer couple numbers to converge. Then we go to Electrons tab. We should define the maximum number of iterations in self-consistent field steps. It should be determined that if the self-consistent field does not converge, it will stop somewhere. Its default value is 100. Thus, we write 100. Then we specify the convergence threshold for self-consistent field to be 10 to the power of minus 6. Then we should define the mixing factor for self-consistent field calculation. The mixing beta, we explained it before. We set it to be 0.3. And also, there are several methods to mixing old and new charge densities. We choose mixing mode to be plain. In the self-consistent field calculation, we don't use ions and also variable cell tab. Thus, we go to the lattice and atoms tab. In the atomic species, we choose atomic label to be C and also atomic mass, that is 12, and then we should upload the pseudo potential that we get from the Quantum Espresso webpage previously. Now we define the coordinates of atoms. The atomic position is obtained from science about the material. We know that in graphene unit cell there are two atoms, therefore we set NaT equals 2. Now we should define the atomic coordinates of these two atoms. From the figure, we can see that if we consider this atom to be at the origin, its coordinate is 0, 0. The next atom is above this with distance equal to carbon-carbon bond that we know its value from paper, that is 1.41. This is the coordinate of second atom. We can add 0.2 angstrom to all of the atomic coordinates. This cuts the atomic not to be on the margin of unit cell. Thus, this is the coordinate of the first atom, and this is the coordinate of second atom. Should write this here. Now our input file is ready. We can see it before run. This is our input file. We have shown it before. You can see various parts of it. Now we can run it. To run, we choose Run tab and then Configure and Run Calculation, and then we choose Apply and Run. We can see this calculation and some iterations here. We can see that after 6 iterations, the run is over, and we see the message of end of run. If we go on the self-consistent field directory, we can see that some files is created. For example, we can see output file. We can extract some information about this file. For example, the Fermi energy is minus 1.4311 electron volts, and the total energy equals minus 22.77 Rydberg. Also, there are other files, for example, error file that is empty. It shows that there aren't any error. This is our input file. This is our pseudo potential file. Also, you can see a file with .save. It contains information about the wave function.